Welcome back to another video, everyone. Today I'm going to be going over the washer method of integration. Now, this is used for when it's a disk method, except when it's rotated around an axis, it doesn't make contact with the axis. It makes a washer, or like a donut, It's got one ring, another ring, but there's a hole in the middle, and so we want to be able to calculate the area of the solid. But if we use the disk method, we'll also get the area of the hole. So we need a way to solve for the area without getting that bit. That's what the washer method is for. The idea behind it is honestly pretty simple. It's basically just the disk method twice, taking the disk area of the bigger thing and taking the disk of the hole, and then subtracting the hole from the bigger thing, and you've got the remaining area. So what does that actually look like in practice? Well, I've got two functions here. We've got x squared and the square root of x. Now these intersect at 0, 0 and the point 1, 1. So let's say we wanted to find the area in between these two curves. This is a pretty easy integral, all right? We just integrate from 0 to 1, and then we've got the function on top as the square root of x, so we'll put that first. And then on the bottom is x squared, so we'll put that next. dx. All right, now we can integrate using the reverse power rule, and it's not too tricky. Square root of x, that's just going to be x to the 1/2. So the new power, 1/2, add 1 to that, you're going to get 3/2. So we have x to the 3/2, and then of course divide by that new exponent, so 2/3, and then minus x squared, that's nice and easy. X squared, 2 plus 1 is 3, divide by 3 in the front, so we have 1/3 x to the 3, and this is of course all evaluated from 0 to 1. Since all the x's, that's all we have, we don't need to worry about the plugging in 0, we know it'll cancel out to 0. So we plug in 1, that's easy, 1 to any power is going to be 1, so it's going to be 2/3 minus 1/3, and that is of course just going to be 1/3 for the final area. Okay, so that's the process for when it's just two-dimensional. Pretty easy, right? We just solved a nice little integral, nothing too complex. You just have to know which function is on top and which function is on bottom in the period that you're looking at. But what if we rotated these functions around the x-axis, like we did with the disk method, and we wanted the volume of the solid created by that rotation by this region? Okay, well, what the heck is that? How are we supposed to figure that out? We can't just do the disk method because we'd be unaccounted, or I guess overcounted, for all of this space. Well, let's use the washer method. We already know which function is going to be the outer ring because it's going to be the function that's on top here. As a reminder, this is square root of x, and this is x squared. All right, so we're going to be integrating, and we know we're going to be integrating from 0 to 1 on x still, so we'll put that. Integrate from 0 to 1. Now, what is going to be on the inside of this integral? Okay, well, if we do the disk method twice, right, employing the disk method, it's pi f of x squared, and that'd be our integral. F of x here is going to be root x, so root x squared is just x, right? And then the idea here is that we're minusing the disk that goes on the bottom, or at least on the inside. That would be the disk created by x squared. So x squared squared is going to be, remember we're subtracting, so minus, x to the 4th. Don't forget, we need the pi in front, and then of course we're integrating with respect to x. Now this is probably an even easier integral than the last one, right? Integrating x, that's easy, it's going to be 1/2 x squared, reverse power rule, right? So we're going to have pi over 2, remember that pi carries over, that's going to be x squared, and then minus x to the 4, integrate that, again it's just reverse power rule, we're going to get minus pi over 5 x to the 5th, and this is of course evaluated from 0 to 1. Now, we don't need to worry about the 0 term because that'll just go to 0. We plug in 1, that's easy, everything is going to be 1 for these x's. So we'll be left with pi over 2 minus pi over 5. Now this, if you just combine the denominators, you'll get 5 pi over 10 minus 2 pi over 10. 5 minus 2 is, of course, 3 pi over 10. And so 3 pi over 10 would be the final answer for this problem, the solid generated by rotating this region around the x-axis. Now, the general formula for this is quite simple. If you have your two functions, say f of x and g of x, where f of x is on top, like we had, square root of x would be our f of x in this case. For the washer method, it's going to be the integral from a to b, that being the two intersection points, whatever these 2 points are that enclose the region. We're going to have the pi in front, and then we're going to have f of x, that's the one on the top, squared, minus g of x, that's the one on the bottom, and that's going to be squared too, and of course it's all with respect to x. It is extremely important that you remember that these are squared individually. It is not f of x minus g of x squared. It is f of x squared minus g of x squared. So that is the washer method. Since you already know the disk method at this point, it's pretty simple. Not going to be a very long video, but I hope you guys enjoyed watching, even if it was so short. And I will see you guys in the next video. Thank you so much for watching.